Welcome you all to this cryo-EM course. Last class we discussed about that different types of detector, and we already discussed about that CCD camera, plate camera, direct electron detector, how they are working and why direct electron detector is required for the cryo imaging. Specially I focused on what kind of camera should we use for negative staining microscope or room temperature microscope. And for the material science also, even if we are using very high electron dose, we mostly do not need direct electron detector. Direct electron detector is very much required if we are using the biological science sample, because biological science sample will be very low contrast and we are using a very low electron dose, and that is the reason we want direct electron detector. So, direct electron detector, it will help us to get a better contrast. So, in this circumstances, let us see that what we discussed so far about that imaging, how it is going to affect. We are talking about the first readout and how this first readout is helping. There are lots of images you can see even in our cell phone also. Lot of time you can see if there is a motion, and if you are trying to collect that image during the motion, that okay. So, if you just consider that one tiger is running and we want to capture that one. So, you can see some of the area, because of this motion it will be very difficult to capture that thing properly because it is under the motion. But those nowadays, even the cell phone also, within that cell phone there is a so high technology they are using. They are not collecting a single integrated images. When you are take the camera and click it, it may be 1 second or 2 second exposure to that particular image. But because of this continuous motion, or if you just consider that you are in a train and through the window you are looking at something and you want to click, and that is the other object is also in a motion. So, due to this motion, most of the time your images will be blurred. So, there will be a proper procedure to correct this that motion. So, we should not see that kind of problem. In the next class I will try to show you some real time examples that will help us you to understand. So, now, what I am trying to say that okay, even in a cell phone, when you are collecting some images and if it is in a motion, what it will do, it will not just collect a 1 second exposure or 2 second exposure and give us an integrated one single image. It will just collect the image very fast, the readout will be very fast, and then it will collect multiple frames. Then even because of that motion, there is some changes between that motion. What it will do, it will correct those motion. So, even there is a shift between this frame and this frame. So, it will bring that motion back and align with this actual frame and try to align most of them and give you an integrated image. We are looking at that integrated image and we are thinking that oh, it is so nice, the contrast is very good. But inside that, when you are collecting data, there is a lot of processing happening, and it is helping us to align those frames in such a way we cannot feel that motion anymore. But if you just have a still camera and the old days camera and you are depending on your and if you are trying to collect these things, it is a big difficult task to correct those motions. Exact same thing we can do it when we are collecting data using the direct electron detector. Okay. So, let me explain that how it is happening. So, that we already discussed couple of times, that how we are collecting the data, how we are preparing the sample. The sample wise, I am just trying to recall the entire process. This is our cryo grid, one particular square, we have multiple holes. Inside that hole, if we look at that hole, inside that hole there will be a buffer and the samples. We quickly freezed into liquid ethane, liquid ethane, and whenever we use that liquid ethane, so if this is our liquid ethane, so what is happening, we have a chamber where the buffer solution was there and it freezed. When it freezed, all the particles are different orientation is there and electron beam is going through there. As I mentioned that generally for electron dose, how much electron dose we are using? We are using 40 electron to maximum 80 electrons per angstrom square, okay, angstrom square. So, that is the electron dose we are always using there. So, if we cannot use more electron dose, because if we use more electron dose, this thermal drift it will be more, and that is also melt this ice. If it will melt that ice, we cannot see that image properly and we can see only the blurry image. That will come back and we will discuss. Not only that, if we just look at, there is a 2-3 possibilities I already explained that, okay, there is a ice can form like that. If we just look at this one, or ice can form like that, right. Now, electron beam is going through this sample. When this electron beam is going through that sample, because of this heat energy, or there is a huge amount of energy transfer it is happening, there is a possibility this same thing there may be a change in the ice pattern. What kind of change we are expecting this the ice pattern? There will be some kind of bulge, it will be bulge in one particular area when the electron beam is there. So, this may be bulged like that. There will be not a uniform shape of this ice anymore. So, there will be some kind of changes in the ice. When there is a change in the ice, that is also changing the position of the our sample, position and the angle of this sample. So, if some sample is fixed in this orientation and other is fixed in this orientation, because of this morphological change of the ice, there will be a rotation of these particles, there will be a movement of this particle. So, we cannot capture actual position of this protein sample or DNA sample or DNA protein sample. That is the reason it is better when the electron beam it will go. If there is some kind of changes, if there is some kind of motion, better to correct it. So, that is one of the reason how we are doing. As I told, we are using the direct electron detector, and direct electron detector readout is very fast. So, even if this 40 electron or 80 electron, we are collecting a exposure time, if you just consider 4 to 8 seconds. So, some cases we are using a longer exposure. Longer exposure means this kind of drift will be much more higher. So, that is one of the reason we are using a shorter exposure time and more electron dose, that may be better. So, if we use a longer exposure means 60 seconds exposure, this kind of drift or this kind of problem, it will be much more. So, now if you just use a 4 second or 8 second exposure, and if you just consider that total electron dose it will be 40 electron, you just consider total electron dose is 40 electron per angstrom square, and now you are just collecting 4 second exposure. So, you can, or 8 second exposure. So, you can tell that you are splitting this 8 second, each frame you are splitting into more. So, here that I will say that, okay, total electron dose is 40 electron and I am collecting 40 frames. So, not one single image, one single integrated image, no. So, this is one single integrated image. For CCD, we are collecting this kind of image, but for our purposes, for cryo-EM purposes, what we are doing, we are collecting one frame, then we are collecting second frame, then third, fourth, fifth, and keep going on, and finally we are collecting. So, if we just give a name 1, 2, 3, 4, 5 and keep going on like that. So, now you consider this is a 37th frame, 37th frame, then this is 38, then this is 39, and then this is 40th frame. So, I have total 40 frames here. So, if we just divide 40 frames means 40 electron by 40 frames. So, per frame 1 electron we are considering. And now, if you have total exposure time, this is our exposure time, right, exposure time. If this is my exposure time 8 second and 40 frames. So, you will get that per frames how many seconds you want to give that. So, 0.2 seconds basically we are giving. So, we are collecting 0.2 seconds per frame. So, each frame we are collecting 0.2 seconds. And now, the total exposure total we are going 8 seconds to collect this entire 40 frames. When you have entire 40 frames, that is a huge size and it is a movie kind of thing. Now, as I mentioned that we are collecting a single frame, that is frame number 1, and then there is a some kind of movement. If I just consider that this is my frame number 2. So, here this is the movement, you can consider that this is a difference. Then third frame there is a more movement. So, something like that, this is the difference between the first frame, second frame, third frame. Now, if I come back and first align 1 and 2 properly and get an integrated image, this is coming 1 plus 2 integrated image. Then my third frame is somewhere here, third frame. Now, third frame I am aligning with this one and trying to get an integrated image from this one, that 1 plus 2 plus 3. Now, this integrated frame we are trying to align with the frame 4 and keep doing these things until we will align all this frame, and then we will get an integrated image. So, here I am just using a very simple way to explain how we are aligning this frame, but actually computationally it is a bit complicated stage. There are a lot of things you have to consider when you will align those frames and do the motion correction. This entire process is called the motion correction. We will collect the data and then we will do the motion correction. This is the first part when we will discuss about the data processing. First we will get the data and then what is next. This is the next step, we will correct the motion of the individual frames and correct the motion first, correct the drift first and get a better image. Let us take a look how this is looking actually. So, here I am showing you some of that frame. So, I collected couple of frames here. So, from this is you can consider this is the frame number 1. In this particular image we cannot see anything clearly. So, there are maybe some spots are here, something is visible here, something is visible here, but this is not very clear at this moment. So, next as I mentioned we are collecting more frames and we keep going on like that. So, we collected more frames. So, like that we are collecting total 40 frames, and based on those features that okay we have some kind of marking here. So, I can see some kind of pattern and I am trying to align that first frame with the second, then second with third or fourth, fifth and keep going on that, and then try to align in such a way and that bring it back and make an integrated image here. When we will make an integrated image here, we can see that this is our integrated image of all of this. So, actual scenario you cannot see any information in this particular image, but When we integrated and corrected the motion, you can see a very clear pattern here, where you have some small protein molecules here. Those small protein molecules, basically those black molecules are the protein molecules here, and this is a cryo image. As I mentioned previously, in the cryo image, protein appears as a black in the comparatively white background. So, these are our proteins. So, this is how we will align the images and it will help us to correct the drift. Now, this is a drift correction tool, and this data is collected at K2 direct electron detector, and this is the drift correction tool. Here we will just show you that how we are correcting the drift. Here this is a power spectrum, and if you look at this power spectrum in one direction, you can see in this particular direction we are losing signal, and we can see some signal in this particular direction. Now, there is a multiple frames, and frames there is a motion between these frames. So, how many frames we have? We have some total 29 frames, okay, and there are lots of parameters are there that we can play around and we can correct. So, this is the drift correction tool that we can use it for correct drift, but nowadays this kind of motion correction tools are available in other tools also, because most of the time when we are use the data processing tool like Reliant, like Eman or like CryoSpark, in all the cases there is a integrated motion correction or drift correction tool is there. So, that will correct, and overall principle is same, and overall outcome you will see the similar kind of things. So, that is one of the example I am showing. During the data processing time, I will show you how those data processing tools like that Reliant, CryoSpark or Eman is correcting those drift. So, in this particular case, this is before correcting the drift. So, drift is not corrected here. Here it is the after correcting, we can see the image, and here you can see individual frames motion. So, this is first frame, then second frame, third frame, how they are moving from one frame to the other frame. So, this is very unpredictable, we cannot predict in which direction it is going to correct, and after motion correction you can see most of the Thorne rings are recovered from the power spectrum, where some of the signals we are losing here. Here we can figure out all this power spectrum and all the signals very after motion correction, all the signals are recovered here. Okay, there is another example I am showing you here, where you can see that the FFT before alignment and FFT after alignment, and there are some microtubules kind of images where you can see this is the movement of these individual frames, and this is the movement trajectory. Now, I am showing you some images where you can see that motion, how this motion is affecting our actual images. So, here this is a image of a virus image before drift correction, and this is a image after drift correction. So, in this particular image it is a without drift correction, and we are making an integrated image. When we have an integrated image, that integrated image you can see that there is some kind of motion, we can see it, and many features of this virus is not very clear. There are lots of lines like pattern, we can see it in all the virus particle. Now, the same virus particle we consider and we corrected the drift. When we corrected the drift, we can see lot of individual features very well distributed all over the virus particle, and it is clearly visible from these two different images. Before drift correction, this is the before drift correction and this is the after drift correction. You can see the difference between these two virus particles and images, and that is basically good enough to tell us that okay, there is a thermal motion or there is a drift when there is a electron beam is going through the sample, and if we correct the drift, it will really improve our 2D images, and if 2D images is improved, that is going to reflect in our 3D reconstruction. Now, there are couple of very nice studies are there. So, those are the virus particle. We use this virus particle because the virus particles are big and it is much easier to see their movement, and if after correction and before correction and after correction it will be very clear. That is the one of the reason we selected the virus particle. Now, we discuss about this particular event that okay, when there is a electron beam is going through that sample or amorphous ice, there will be some changes, right. So, here first let me explain what is happening here. This is the hole we are talking about, that cryo hole we are constantly talking about, this is the hole, and this is the carbon area where we want to focus, and those are the amorphous ice inside that hole, and those are the individual virus particles. Most of the times virus particle will try to stay near the carbon area. If this is the carbon area, they will try to stay, because the ice thickness near the carbon area it will be much thicker than the central part, because central part will be comparatively thinner ice. Now, if you look at the next, the same hole we are constantly imaging. So, what we are doing, this is a hole, as I mentioned, if this is your hole, if you are adding sample, it will be a buffer solution, and protein it will well distributed inside the hole, and this entire thing you are plunging into liquid ethane. When you plunged into liquid ethane, it will form the amorphous ice, that you are basically can see it here, the amorphous ice and the virus particle. Now, if you look at the top, what you can see? You can see different kind of electron dose exposed this same hole, where we have a same virus particle, we are exposed it for 8 seconds, 8 electron per angstrom square, 16 electron per angstrom square, 24 electrons per angstrom square, and 32 electron per angstrom square. Now, what we can see at the bottom, the figure number E. So, you can see the trajectory of individual virus particle, how they are moving inside the ice. So, that is basically we are constantly telling that when there is a electron beam has lot of energy, it will interact with the protein sample and protein will start spreading in a different direction. So, that is basically we can observe here. We can see that some of the particles there is almost zero motion. If you consider this particle or this particular particle or this particular particle or this particular particle, there is no motion, but some of the particle there is a huge movement. Some of the particle has a very limited motion. So, that is one of the reason I told that when there is a electron beam interaction with the protein sample or any biological science sample, we cannot predict at what kind of motion do we can see, and that you can see in the previous image also. If you look at here, you can see the movement of the frame. These are telling you the movement of the different frame. Here we have total 40 frames. Some frames the movement is very high, and then there is a movement is very less, and then again drastically there is some movement, again movement is less. So, it is very difficult to predict what will be the movement of those virus particle or the protein sample. One thing you should remember, that if the sample size is bigger like the virus particle or the liposome, they are really big size, their movement will be comparatively less. If there is a small protein, their movement will be huge, that we are going to discuss in the next class. Now, when we are going for a longer electron dose, this movement will gradually increase. You can see that the movement for the 8-second electron, 8 electron per angstrom square or 32 electron per angstrom square, there is a drastic change, because you can see the movement is much higher when you are using 32 electrons per angstrom square. So, you can see most of the particles is moving, some of the particles is moving this direction, some of the particles are moving this direction, some of the particles is moving this direction. So, this movement is very random when they are staying inside the ice. Now, if you just focused at the high mag, you can see what I was trying to explain, that okay, these are the virus particle. Some of the virus particle, this is the carbon area. This is the same image, we are targeting one particular area. If you just consider that okay, this is the carbon area as I mentioned, and this is the hole where virus particles are there. Now I am targeting this particular area to collect the image, because my sensor size is only image this much. It cannot image this entire hole, because we have to go a very high mag and collect this data. So my sensor can capture only this much area. So that is basically, you can see it here, you can see some part is carbon, and these are the ice area where virus particles are embedded. Now if we are targeting individual virus particle, what we can see, some of the virus particle, those are the virus particle close to the carbon. So some of the virus particle like this one, this and this has a higher motion, where those two virus particle has almost zero motion. This virus particle has some motion, but direction is different. When we are putting this, it is showing the direction is this. When we are showing this, the direction, it is starting the center here and movement is this direction. So this is the another image where we collected. So you can see the movement of the virus particle is random. So some movement is this direction, some movement is this direction. There is no uniform motion of this virus particle. So that is one of the reason whenever we are doing data processing, that we have to do a motion correction and getting a high resolution features. So if you see that all the time whenever we are collecting data, there is some kind of movement that is going to affect our power spectrum. Probably low frequency signal which is centered at this particular area, it is not going to affect that much, but whatever signal is coming from the high frequency signal, that is going to severely affect. So that is one of the major reason that drift correction or motion correction is a very important part. As I mentioned, if you are just targeting a bacteria, only the image of a bacteria or a virus, even if we do not do the motion correction, it is not going to change too many things. But in this particular case, if we do not correct the motion, so there will be lot of side chain features, or the helix or beta strand will be scrambled, and it will be very difficult to identify the individual helix or beta strand, because there is a lot of random motion and we are trying to put all of them together to get a high resolution structure, which is not possible. That is the reason whenever we will get a cryo data, if we want a high resolution structure, we do the motion correction first and then go for the next step. So here I am showing you some cryo data of a virus, the bacteriophages images, where you can see there is a huge bacteria head and the bacteria tail. Those images are collected in our facility, where you can see those are the DNA molecules. Here you can see some of this adenovirus structure also, which is, this is the carbon area, and those virus particle after drift correction you can see this is the well distributed. There are 4 virus particles are there. A lot of time you can see outer spike protein also in these adenoviruses. So this is some of these images after drift correction, before drift correction I showed it. Now we are constantly bringing that topic, that high frequency signal, low frequency signal, then power spectrum. What is the meaning of those things? How we can connect the image with a power spectrum or low frequency signal, high frequency signal? That will be our next topic. We are going to discuss those things. Today we will finish it here, that entire microscope anatomy, and so starting from electron gun to detector, how we can collect a good data, as well as I also mentioned how we can do the motion correction, why it is important, how it is affecting our high resolution signal. So those parts, some of this part we are going to repeat again when we will start the data processing. Thank you all for your attention. We will discuss rest of the part in next class.